All right, guys, we've got a lot of new theorems here in this lesson on secants, tangents, and their angle measures. And we really need to prove them to be super comfortable with them. So this first one that we looked at, circle theorem 12, tells us that if two secants intersect inside the circle, then the angles they form are equal to 1/2 the sum of the arcs that they intercept with their vertical angle. In other words, this angle 1 here equals 1/2 the sum of these two arcs here that this angle is intercepting with itself and with its vertical angle. Okay, how do we know this is true? How can we be confident of it? Let's tackle a proof of this. All right, here's our circle theorem 12, and don't forget, when you do a proof, basically what you're doing is you're taking this conditional statement that is the theorem. If this, then that. We've got if, hypothesis, then conclusion. And it's our hypothesis that is our given information. And it's our conclusion that is what we're being asked to prove. So this, after the word then, is our conclusion. Prove that the measure of the angle formed is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. So what we want to prove here is that the measure of angle 1 equals 1/2 times the sum of the measure of arc RU and the measure of arc ST. Okay, just going to write that out. Okay, that's what we're being asked to prove. What's the given information? That's our hypothesis. Two secants are chords intersecting the interior of a circle. So I'm going to say that secants RT and SU. And since those are secants, I'm going to give them 2 arrows over the top. Sorry, this is a little sloppy, but I'm trying to save room because, as you can see, this might take a little bit. Secants RT and SU intersect in circle C. Good. So that's our given. All right, where are we going from there? Well, I'll give you some hints. We're going to use inscribed angle theorem, which we've already proven that we're comfortable with. We're going to draw some auxiliary lines. And first auxiliary line I want to draw UT. Why am I drawing UT? Okay, I'm just going to say draw auxiliary line UT. I actually drew a segment, so we'll call it line segment UT. The reason is 2 points define a line. 2 points define a line. Good. Okay. Actually, I think that is all I need. I just need one auxiliary line. Here's where I'm going with this. I'm going to point out that this angle SUT, the measure of angle SUT, equals 1/2 the measure of arc ST that it intercepts. Okay? How do we know that? Well, that's our inscribed angle theorem that we proved. If you haven't seen that video, go back and check that one where we prove all the conditions of our inscribed angle theorems. That was actually our condition 3 that we did, but that works. Okay. Likewise, angle RTU, the measure of angle RTU, is going to equal 1/2 the measure of this arc RU that it intercepts. Okay, same reason. Inscribed angle theorem, right? Okay. Now I'm going to drag you all the way back to chapter 5 in relationships in triangles. And I'm going to throw out the word exterior angle. Anybody see an exterior angle in a triangle here? I see a triangle right there. I see angle 1, which is like right up there in our dashboard, right in our GPS. This is part of our destination. Angle 1 is an exterior angle to this triangle, is it not? And what do we know about exterior angles and triangles? We know that the exterior angle, measure of angle 1, is going to equal the measure of angle SUT plus the measure of angle RTU, right? Aren't those the two remote interior angles? in that triangle, and the exterior angle always equals the sum of the two remote interior angles. Good. That's our exterior angle theorem. I might not need as much space as I thought I was going to for this. Okay. Anybody see where we're going there? Anybody see any substitutions? Maybe some factoring we can do? We know that the measure of angle SUT is this, and the measure of angle RTU is that. Could we substitute them in and get the measure of angle 1 equals 1/2 the measure of arc ST plus 1/2 the measure of arc RU? Good. What did we do there? We just used a substitution. Since we already proved that those quantities were equal, now we can substitute them in for those. Okay. Look at that. Every now and then you want to, of course, look back at your GPS and see, are we approaching our destination? How would I get from here to here? Do I just need to factor out of 1/2? I think that's all we got to do. The measure of angle 1 equals 1/2. We're going to factor out that 1/2, and what's left over is the measure of arc ST plus the measure of arc RU. What did we do? We factored it out. What do we call that? I don't know if you guys noticed, but in one of my other videos, probably it was the Inscribed angle theorem video, I misspelled the word distributive. I think I spelled it distributive. It's hard to talk and spell at the same time. Okay. All right. Did we prove this theorem? Did we arrive at our destination? Shall we drop some Latin on it? QED. All right, another theorem that we learned, circle theorem 13. If a secant and a tangent intersect at the point of tangency, then the measure of each angle formed is 1/2 the measure of its intercepted arc. So this angle 1 that's formed by this secant and this tangent has half the measure of this arc RST that it intercepts, and this angle 2 has half the measure of this arc RT that it intercepts. Okay, how do we know this is true? Let's prove it. All right, I can think of two ways to prove this. I'm going to show you what I think is the simpler one first. First, let's go ahead and set it up. Remember, if a secant and a tangent intersect at the point of tangency, that phrase after the word if is our given information. That's our hypothesis, right? So a secant and a tangent intersect at the point of tangency. So we could say we have secant RT, right? And we have tangent T. Or tangent, we're going to have to give it a name. That's point T. Let's call this L. And tangent L. Good. That's our given. Okay. And what are we being asked to prove? This bit after the word then. That's our conclusion. The measure of each angle formed is 1/2 the measure of its intercepted arc. Let's work on angle 2. Okay. So let's say the measure of angle 2 equals 1/2 the measure of arc RT that it intercepts. Okay. All right. So the way I want to prove this is I want to just drop just a point here on the tangent, and I'm going to call this point point U. Okay. So that I can draw auxiliary line RU. Okay. I'm just going to do that. All right. So I'm going to draw auxiliary line RU from point R to point U on tangent L. Okay, and I'm doing that because why? Because I can, because 2 points define a line, right? Good, I can do that. All right, and because this necessarily crosses a circle, I'm going to go ahead and label this point of intersection. I'm just going to call it W. Let's call that W. Okay, and so point W is at the intersection of RU and the circle. Okay. And why am I doing that? Where am I going with this? Well, exterior angle theorem, right? Anybody see it? Thinking angle 2 is an exterior angle to this triangle that just popped up on our page, right? So could we say that the measure of angle 2 equals the measure of angle RUT plus the measure of angle URT? Are those the two remote interior angles, right? This is our exterior angle. These are the two remote interior angles. So this is exterior angle theorem, right? Good. Okay. It also looks like that this line RU is a secant, isn't it? So if I've got a secant and a tangent intersecting outside the circle, there's other theorems that we know. I know I haven't proven those yet. I'm going to prove those next. But, once you've proven them, you can use them. So could I say that the measure of angle RUT equals 1/2 the difference of the measures of the intercepted arcs, right? So the measure of angle RUT is going to equal 1/2 the difference of arc, the measure of arc RT minus the measure of arc WT. And that's why I put W on there, just so that I could refer to this arc. That's really the only reason we had to do that. Okay, so this is our theorem. I'm going to call it, I'm just going to call it circle theorem 14. Just for abbreviation, okay? And we're going to prove that one next, okay? But we're using it. Okay, so if the measure of angle RUT equals 1/2 the difference in these two arcs, we could end up substituting that in there. What else do we know? I'm looking at this angle URT, right? And I'd like to say that the measure of angle URT equals 1/2 of what? URT is an inscribed angle. Isn't it going to equal 1/2 the measure of its intercepted arc, WT, right? Okay. So it looks like I've got expressions here in relation to the arcs that I could plug into this equation that I wrote right here. So I could say that the measure of angle 2 equals, instead of the measure of angle RUT, I'm going to substitute this in 1/2 times the, and I'm going to go ahead and distribute that, if you don't mind, just to save space while we're doing this. I'm going to distribute that 1/2 equals 1/2 the measure of arc RT minus 1/2 the measure of arc WT. I want to make sure I get all these letters right. And then I'm going to go ahead and add in the measure of angle URT, except I'm going to substitute in for it. What do I know? Add in 1/2 this arc WT. Good. What I did there was just a substitution. Oops, I forgot a reason. Substitution. There we go. I forgot. This is inscribed angle theorem, right? The reason for that last statement, inscribed angle theorem. Good. Okay, so we did this substitution. Does anybody see how this could simplify? The measure of angle 2 equals 1/2 the measure of arc RT minus 1/2 the measure of arc WT plus 1/2 the measure of arc WT. Don't these two terms cancel? Or you could say they equal 0, so let's substitute 0 in for them, right? The measure of angle 2 equals 1/2 the measure of arc RT. Good. What did we do? We did another substitution. Okay. Are we ready to convict? Do we have enough evidence? Look at that. we've arrived at our destination. So QED. All right, that's one way to prove this. You want to try another one? All right, I know another proof here that you might find interesting for this same theorem. This one doesn't require us to use this theorem 14 that we haven't proven yet. So you might say, hold on, Mr. Rogers, can you prove it without theorem 14? Yeah, we can do that. Let's try this. I'm naming the circle C, giving it a point C at the center. I'm dropping this point W on this line L, this tangent L, just for reference because we may need it. And the first thing I'm going to do is draw some auxiliary lines. I'm actually going to draw auxiliary line segments that happen to be radii, CT and CR. Okay, so I'm just going to draw radii, CR and CT. Okay, and we can just say, 2 points, define a line, right? We can drop in auxiliary whatever we want, anytime we want. Okay, and now what could you say about, well, first of all, what can you say about CR and CT? Are they congruent to each other? Well, sure, because all radii are congruent. Good, and that's proving that. And that's helpful, I think, because now what type of triangle do we have? We've got an isosceles triangle. So we could state that this angle CTR, the measure of angle CTR, equals the measure of angle CRT. The reason is, if you want to just put isosceles triangle, that covers it, right? The base angles in isosceles triangles are congruent. So they're going to have the same measure. Okay, where do we want to go from there? What can you tell me about this angle CTW? The measure of angle CTW is going to be what? What do we get when we draw a radius to a tangent at the point of tangency? We get a right angle. So the measure of angle CTW is 90 degrees. How do we know? Well, that's our definition of tangency, right? That's a theorem that we've proven. Okay. Where are we going to go from there? I notice that the measure of angle 2 plus the measure of angle CTR equals 90, right? Is that angle addition postulate? I'm just going to add those up. Angle addition postulate, good. You know what, I'd like to have that in terms of angle 2 because I'm just looking at my dashboard, my GPS, keeping an eye on my destination, and knowing that I'm going to need the measure of angle 2 somewhere, I'm going to go ahead and subtract the measure of angle CTR from both sides. So I have the measure of angle 2 equals 90 minus the measure of angle CTR. Okay, I just did a subtraction there, right? Good. All right, where are we going to go from there? Could I get some expression that represents this angle CTR? If this is an isosceles triangle, is it safe to say that if I were to divide, take 180 degrees and subtract out this angle RCT, and then divide it by 2, wouldn't I have each of the base angles because of triangle sum theorem? Maybe we should write that out to make it more clear. The measure of angle CTR plus the measure of angle CRT plus the measure of this angle RCT, let's call it, equals 180. And that is triangle sum theorem, right? Okay, and since the measure of angle CTR equals the measure of angle CRT, I'm going to go ahead and substitute that in. I'm going to substitute in, I'm going to skip a step here to save a little bit of space because you can see this is going to take up some space. I'm going to substitute in the measure of angle CTR for this, and then I'm going to combine them so I've got 2 times the measure of angle CTR plus the measure of angle RCT equals 180. just did a substitution, right? And I think I'm going to do a subtraction now. I want to get this in terms of the measure of angle CTR. I'm going to subtract the measure of angle RCT from both sides. So 2 times the measure of angle CTR equals 180 minus the measure of angle RCT. Okay, I just did a subtraction. Now to really get it in terms of this angle CTR, I'm going to divide both sides by 2. So we get the measure of angle CTR equals 1/2 times this quantity, 180, minus the measure of angle RCT. Okay, it's really division, because multiplying by half is the same as dividing by 2, right? Okay, where are we going here? I'm going to go ahead and distribute that 1/2, just because I can. Measure of angle CTR equals 1/2 times 180 gives me 90. Okay, you can see kind of why I'm doing that, because we got another 90 hanging out somewhere that may cancel. And minus 1/2 times the measure of angle RCT. Okay, that's just distribution. Okay, now we've been kind of dancing around this. What's the significance of this angle RCT? If only I could relate it to this arc RT. Is there any relationship there? Could I say that the measure of angle RCT equals the measure of this arc RT? How do I know that? How do I know that this angle has the same measure as this arc? Well, it's a central angle, right? Central. So that's our central angle theorem. Good. Okay. Geez, maybe I could substitute that in, and then we're starting to get somewhere with this. This is starting to look like our destination. Since the measure of angle RCT equals the measure of arc RT, I'm going to substitute that in and say that the measure of angle CTR equals 90 minus 1/2 times the measure of arc RT. Just a substitution, right? Good. All right, where are we going with this? I think we're moving over to this second part. Do we have an expression for the measure of angle 2? We do. And do we have this expression that contains this thing here? And do we have an expression for this angle CTR that we could plug in here? Look at this. Can we go ahead and put, I'm absolutely going to just highlight these 2 lines and see if anything jumps out at you guys. Okay. Could I go ahead and suggest that the measure of angle 2 equals 90 minus the measure of angle CTR? Now you got to be careful here. If I'm going to substitute this expression in for the measure of angle CTR, and I've already got a minus sign, I'm definitely going to want to open my parentheses here so I get this whole quantity. Yeah, you're going to want to watch out here. If you don't do that, you'll end up with a negative at the end that you can't get rid of. Good. Okay. So measure of angle 2 equals 90 minus this quantity, 90 minus 1/2 the measure of arc RT. Okay. Hopefully you remember this from Algebra 1, the way to get rid of these grouping symbols when you're subtracting some quantity. Oh, first of all, I have to justify this, right, with substitution. Can we go ahead and distribute a -1? There's an implied -1 there. Can we go ahead and distribute it so that we can get rid of those grouping symbols? Right, so we get the measure of angle 2 equals 90. If I multiply 90 by -1, I get -90. If I multiply -1/2 by -1, I get +1/2. Measure arc RT. Good. And the grouping symbols are gone, and all we did was distribute, right? All right, you guys like this proof yet? Yeah, this is a fun one. Okay, 90 minus 90. That is really nice. That just goes away. 90 minus 90 is 0, so I can substitute in 0 for it, and I get the measure of angle 2 equals the measure of arc RT. Substitution. Take a look at our dashboard. Are we there? You have arrived at your destination. See that? I think I like that other proof a little better. It's a little quicker. are we ready for the big kahuna here? Circle theorem 14. We've got these three conditions. We've got to prove these. Basically, circle theorem 14 tells us that if two secants, or a secant and a tangent, or two tangents intersect at a point outside the circle, then the angle they form equals 1/2 the difference in the measures of the arcs they intercept. Okay, so can we go ahead and prove this? Let's tackle this condition first. Two secants. Let's see if we can prove this. Okay, let's try this condition first. I've already set it up. What we're being asked to prove is that the measure of angle E equals 1/2 of the measure of arc JK minus the measure of arc FG. Okay, and we're given circle C with secant EJ and EK. So let's go ahead and tackle this. First thing I'm going to do is I'm going to hit it with an auxiliary line. Surprise, surprise. Mr. Rogers, you love those auxiliary lines. Well, they're very helpful in certain proofs. So I'm going to go ahead and draw auxiliary line GJ. Okay, and 2 points define a line, right? All right, where are we going with that? Okay. Well, I see that this angle FJG is an inscribed angle intercepting this arc FG, and I think that's going to help us. I'm going to call it angle EJG, okay, because I want to relate it to this triangle. We've already created a triangle, and we know there's going to be useful information there. So I'm going to say that the measure of this angle EJG equals 1/2 the measure of this arc FG. Okay, and you can think of it as we're collecting pieces of the puzzle. That's the picture we've got to put together. We've got a piece of the puzzle here. We've got arc FG pulled into it. How do we know this? Well, that's our inscribed angle theorem. All right, we proved that. We're happy with it. We can use it. Good. You know what else I notice? I think we can rope in this arc JK. And I think we could state that the measure of this angle JGK equals 1/2 the measure of this arc JK. Good. That's also inscribed angle theorem, isn't it? That's an inscribed angle. Good. I think this angle JGK has some relationship to this triangle EJG, right? This triangle here. Could we say that the measure of angle JGK equals the measure of angle E? Look at that, I'm pulling in another piece of the puzzle. This angle is going to equal the measure of angle E plus this angle. How do I know that? Plus the measure of angle, what did we call that guy? EJG. Okay. How do we know that? That's our exterior angle theorem. If you just want to write exterior angle. This guy is an exterior angle to this triangle, so he's always going to equal the sum of the two remote interior angles. And there they are. Those are the two remote interior angles. Okay. All right. I sense something here. What do we know about the measure of angle E? Could we solve this for the measure of angle E? Yeah, I think we could subtract the measure of angle EJG from both sides. And I'm going to do a little symmetric property on it at the same time just to clean it up. I'm going to say the measure of angle E equals the measure of angle JGK minus the measure of angle EJG. I just did subtraction, right? Okay. All right, where are we going to go from there? I'm sensing the substitution. Anybody feel the substitution coming on? We know this angle JGK can be related to this arc, and we know this angle EJG can be related to this arc. Can we go ahead and substitute those in? The measure of angle E equals, if the measure of angle JGK equals this, I'm going to plug it in for that. I'm going to substitute it 1/2 the measure of arc JK. Good. Minus, I know the measure of angle EJG equals this quantity, 1/2 the measure of arc FG. Substitution. Man, this one was even easier than the last one, surprisingly, huh? Anybody see where we're going from here? How to get this to look like that? Do we simply have to factor out a 1/2? We get the measure of angle E equals 1/2 times the measure of what's left over after we factor out a 1/2. We're left with the measure of arc JK minus the measure of arc FG. Good. What did we do there? We did distribution. Your destination is on the left. QED. Good. Okay, could we prove this condition where we have a secant and a tangent intersecting in a similar manner? Can we prove that this is still true? The measure of angle E equals 1/2 the difference in these two arcs, JG minus FG. Okay, well, yeah, I think we can. And I think it's a good thing we proved that circle theorem 13. We got really, really comfortable with it because I think we're going to use it here as one of our reasons. Hopefully you see it, right? Did we just draw an auxiliary line, GJ? Draw auxiliary line, GJ. And that's because 2 points define a line, right? And the significance of that is it's a secant that intersects a tangent at the point of tangency, right? We just proved that theorem. Good, so we can use that. And we can say that the measure of this angle JG, oops, I'm going to need some point. I'm just going to throw in a point W there, okay, just for convenience. The measure of angle JGW is going to equal 1/2 the measure of this arc JG, right? Okay, how do we know that? Well, that's, I'm just going to abbreviate it, I'm going to call it circle theorem 13, the one we just proved. Okay, you could say when a secant intersects a tangent at the point of tangency, the angles formed are 1/2 the measure of the intercepted arcs. That's a mouthful. Let's just call it circle theorem 13. Good. What else do you notice here? You notice this angle EJG, measure of angle EJG equals what? Is it related to this arc FG? It's going to equal 1/2 the measure of this arc FG. Good. Okay. All right. How do I know that? That's our inscribed angle theorem. Inscribed angle theorem. We'll call it inscribed angle. Good. Okay. I also know something about this angle JGW. I know the measure of angle JGW is going to equal the measure of angle E plus the measure of this angle EJG, right? How do I know that? This angle equals the sum of the two remote interior angles in this triangle. Because it is an exterior angle, that's our exterior angle theorem, right? Good. Okay. Look at that. We've got lots of pieces of the puzzle we're looking for. Could we go ahead and solve this for angle E so that we're all fixed up on the left side? Let's subtract the measure of angle EJG from both sides, and I'm going to do a little symmetric property on it again. The measure of angle E equals the measure of angle JGW minus the measure of angle EJG. That's subtraction. If you want to point out that you also use the symmetric property, you can, but I think we're good with that. Good. Okay, I'm feeling some substitution coming on. Anybody see it? That angle JGW could be written in terms of this arc JG. Could we write this as the measure of angle E equals 1/2 the measure of this arc JG minus, what do we know about angle EJG? We know it is related to this arc FG. It equals 1/2 the measure of arc FG. Good. Is that a double substitution? Substitution? Yeah, absolutely. How do we get that to look like that? You can sense we're almost there. the measure of angle E equals, let's go ahead and factor out that 1/2, right? 1/2. We're left with the measure of arc JG minus the measure of arc FG after we factor out that 1/2. What property is that? We call it distributive property, but we're actually undistributing, aren't we, when we do that? Okay. All right. Does that look like that? Absolutely. Send it. All right, last one. Can we prove this last condition where two tangents intersect outside the circle? I've already set this up. What we want to prove is that the measure of angle E equals half the measure of arc FJG minus the measure of arc FG, half of that quantity. And we're given these two tangents, EF and EG in circle C. So let's go right ahead. If you've been paying attention, you probably suspect I'm about to hit this problem with an auxiliary line from F to G, right? Let's go ahead and draw that auxiliary line, F, auxiliary line, FG, and that's because two points define a line. I'm just going to say 2 points for now, okay? Okay. Some interesting things going on here. We do have this exterior angle, this the measure of this angle FG. Oops, I'm going to need that. I'm going to need that point W again, right? The measure of angle FGW is going to equal 1/2 the measure of this arc FGJ, or FJG, excuse me. Got to get my letters in the right order. How do we know that? That's that theorem we proved where the secant intersects the tangent, right? And what did we call that? That was circle theorem 13. Again, if you want to say that when a secant intersects a tangent at the point of tangency, then the two angles created are each equal to 1/2 the measure of the arcs they intercept. You can write out that novel if you want, but if you want to say circle theorem 13, that's fine. Okay, and then we also have the measure of this angle, because this is another tangent. We could say the measure of this angle EFG, right? EFG equals 1/2 the measure, oh, I forgot to put the measure in there. Okay, 1/2 the measure of this arc FG. Good. Okay, how do we know that? That's also circle theorem 13. We're using it twice this time because we got two tangents. Okay, good. And I think we also know that this angle FGW is an exterior angle to this triangle. So the measure of angle FGW equals the sum of this angle E. The measure of angle E plus the measure of this angle EFG. EFG. The reason is, for this angle here, this exterior angle in this triangle, the two remote interior angles are these guys right here. Exterior angles always equal the sum of the two remote interior angles. Okay, that's our exterior angle theorem. Exterior angle theorem. Good. Okay, and again, you know what? I'm going to go ahead and solve this for angle E so that we can get towards our destination. I'm going to say the measure of angle E equals the measure of angle FGW minus the measure of angle EFG. We just did a subtraction there, right? Subtraction. Okay. By the way, well, as I'm doing this, you guys may be thinking of different ideas here for proofs, and there can be many, many different ways to prove the same thing. You might also notice that since these are two exterior tangents drawn from an exterior point, you might notice that those are congruent, and then, I got an isosceles triangle. Maybe there's other ideas there. I'm not going to go there, but maybe that's a faster way to prove it, or maybe not. I don't know. But if you're trying to prove this, you might want to notice those things and plug in as much as you know and see where it takes you. For now, I'm going to continue on with my idea of just kind of substituting in these expressions for these arcs that we know. We know the measure of angle FGW it happens to equal 1/2 the measure of this arc FJG. Good. And we happen to know that this angle EFG equals 1/2 the measure of this arc FG. Okay, and all we did there was a substitution, right? And then again, deja vu, we can factor out that 1/2. 1/2 times what's left over after we factor out the 1/2? Measure of angle FJG minus the measure of arc FG. Yeah, I'm starting to get fried here. What did we do here? Distribution. Yeah. Okay. Does that match what we were being asked to prove? Absolutely. Q, E, D. Good. All right. That is my proofs for the circle theorems in this last lesson on secant, tangents, and angle measures. I hope you guys found them helpful. Feel free to pirate some of these ideas if you happen to have homework problems that ask you to prove some of these theorems. Pirate these ideas, but also feel free to try to come up with your own. For instance, like I suggested here, there's other things that we know when we draw these auxiliary lines, and all of the geometric theorems we've learned throughout this course will help you to do these proofs. Maybe you'll come up with a proof that nobody's ever done before. All right. Good luck, guys. Thanks for watching.